Thank you for the introduction and the opportunity to present this work at the Peer Review Congress. I'm a first-year MD PhD student. I would like to thank all my co-authors as well as everyone at the Health Information Research Unit, or HIRU, for making this work possible. So, as many of you know, considering the number of published literature, it is impractical for clinicians to keep up with the most up-to-date evidence. The Premium Literature Service, or PLUS, hosted by HIRU, is a gold standard service for more than 30 years in disseminating evidence to clinicians. Specifically, we retrieve articles from approximately 120 journals daily. Subsequently, we manually classify these based on their publication type as well as purpose. We then manually appraise them using our custom tools, and those that are of sufficient quality and clinical relevance are disseminated to subscribers worldwide. However, considering the increase in the published papers every year, this process has become more time-consuming and costly. And for this reason, HIRU has been experimenting with machine learning to partially automate this process. So one of our previous experiments published in the journal Biomedical Informatics focuses on the appraisal of original treatment, primary prevention, or quality improvement articles. So specifically, we took these articles, the titles and abstracts of these articles from PLUS and Clinical Hedges, which is a similar database that preceded PLUS to train encoder-only transformer neural networks. To be rigorous, these articles must be RCTs with relevant clinical outcomes, have adequate sample size and follow-up, as well as pre-planned subgroup analyses, if any were done. And the best performing model, which was a BioLink-BERT model, achieved an AUROC of 89 to 95%. And based on these results, we concluded that these models have strong potential in assisting in the workflow. However, despite recent architectural advancements that led to massive improvements in natural language processing, there has been less focus on the transparency of AI. For deep learning models specifically, if we give an instance, all it gives us is a probability of that article being in the rigorous class. And transparency in AI is important for numerous reasons, including technical scrutiny to detect biases and overfitting, to improve trust amongst stakeholders, as well as to translate knowledge for better efficiency, as well as training of new researchers. And in general, there are two methods for interpretable AI decisions. The first is using a relatively simple architecture, such as logistic regression, that have weights assigned to each feature for prediction. However, these models typically do not perform too well on natural text. For deep learning models specifically, we often resort to retrospective explanations using feature attributions, where we use algorithms to calculate and assign a numerical value to each of the features that represent how important they are to the model's outcomes. And more recently, there have been numerous explainable AI frameworks with different theoretical foundations that have been developed. However, to our knowledge, there's not yet been any work that looks at explaining a deep learning model over a large text data set. And for this reason, we wanted to see how the applicability of an existing framework on our BioLink-BERT model. So regarding the methods, we trained 630 classifiers using different combinations of pre-trained weights, class weights, batch sizes, and random seeds. And we trained using 43,000 articles from PLUS, and then we tested and validated these articles using 12,000. These models using 12,000 articles from PLUS and 7,000 articles from Clinical Hedges. We then generated the feature attributions using the SHAP algorithm. So for a language model like BioLink-BERT, text is split into tokens. So tokens are either words or subwords that act as features for prediction. So for BioLink-BERT specifically, the max number of tokens it can use is 512, which is around 400 words. And for the explainer, we used a variant of the SHAP algorithm called the partition explainer. And this is because 512 features would be computationally infeasible. And what partition explainer does is that it will cluster tokens together to reduce the computational complexity. And for this work specifically, we back transform tokens into words and sum their feature attributions to improve the interpretability of the results. So before I get into the results, I'd like to briefly go over the theory behind the SHAP algorithm. So if we have a binary classifier and we give it an instance, it will return to us the probability of that instance belonging in the positive class. What SHAP does is that it will mask certain features from that instance and pass it to the model. The masked version is called a perturbation or a perturbed instance. SHAP then sees how the model's predictions, the predicted probability changes versus the original instance. And this difference in predicted probability is called marginal contribution. SHAP does this with all possible feature subsets and averages their marginal contributions. The final numerical value is called a SHAP value, and it represents the feature attribution, or essentially, like I previously mentioned, how important that feature is to the model's prediction. In terms of results, we analyzed 6.2 million words from all titles and abstracts, of which around 49,000 are unique. So the bar plot shows the top 15 most impactful words with 100 or more occurrences for both the rigorous and non-rigorous class. So keep in mind that red and blue in this case means hot and cold. And in this context, red means that a word is associated on average with an increase in the predicted probability in the rigorous class. So now taking a look at the bar plot, we can see words like non-inferiority and randomized, on average, increasing the probability that an article is being classified as rigorous, while words like non-randomized, retrospective, and pilot having negative impacts. So we can see that these terms generally align with our manual appraisal criteria. However, words apparently unrelated to the criteria, such as theotropium, also had sizable impacts, indicating that they may have been correlated with rigor during manual appraisal. And these patterns were picked up and applied by the model. And this may indicate that there is a certain degree of overfitting. So for individual instances, titles, and abstracts, we can associate highlighting with feature attributions to visualize important terms that affects a model's prediction. So here I have two articles, the first of which has a predicted rigorous probability of 96%. And we can see that SHAP identified the randomization process, the mortality outcome, as well as the sample size as important positive contributors. For the second article, with a predicted probability of less than 1%, terms related to cohort studies, such as cohorts, retrospective, as well as propensity score matching, were important negative predictors. So to summarize, SHAP allows us to peek inside a deep learning model and potentially identify important features for its predictions. And the study highlights the practical utility of SHAP for improving the transparency of biomedical text classification. So in terms of implications, when these models are deployed in the real world, it is important when we monitor the explanations, it can provide us with reassurance that these models are actually using and applying meaningful patterns that's consistent with expert appraisal. And for individual instances, these highlighting can improve the efficiency of manual appraisal by potentially indicating important terms. And for these reasons, Hairu has been piloting the implementation of explanations alongside its models. And based on our results, we do recommend that systematic review or knowledge translation platforms that leverage machine learning in some way do consider implementing an explanation, some form of AI explanation for their models as well. So there are important limitations for this work, several of them. The first is that both the models and explanations were trained and tested on titles and abstracts only. This is primarily due to architectural and resource limitations, and it limits the generalizability of our methods and results to full text articles. And additionally, this work is primarily focused on PLUS's datasets, including the articles and also the criteria. While it is not unreasonable for us to assume that the same methodology would also be able to apply to a different tool like the Cochrane risk of bias, but the lack of publicly available data set still remains an issue. In addition, our explanations are localized to the set of articles only, and we don't necessarily know how the model will behave on a different set of articles. Typically, this is only explorable through a global explanation framework, and which has not been widely researched yet. And in addition to that, we have not evaluated explanation faithfulness. And because of this, we cannot necessarily conclude that there is an issue with model training when there is a poor explanation. And practically in these cases, we have to scrutinize model predictions. And last but not least, we have not yet tested the user acceptability of such a system in the real world. So despite promising results, nuances in the implementation as well as deployment remains unclear. And we believe that these are promising future directions for additional research. And thank you very much for your attention. I welcome your questions or any additional clarifications. If you have any additional ones after the presentation, feel free to reach out to me or Dr. Cynthia Locker, who is the corresponding author of this work. Thank you.
Thanks for a great talk. We'll start in the front here.
Thank you for this really interesting work, Leah Welty from Northwestern. I'm wondering if you've considered repeating the analysis, but where you stratify by study design, because I can't help but notice that some of the words that get picked out as positive or negative are very much associated with study designs that might be considered more or less rigorous. For instance, propensity scoring often goes with something observational, of course, and that may be less rigorous. But if you're doing an observational study and you're propensity scoring, my bias is to think that's probably more rigorous compared to other observational studies that do not.
This is a very good question. I'm glad you brought it up. Just to clarify that the data set that we used initially includes both observational and trials. And being a RCT is part of the criteria that we use that considers an article being rigorous. So to answer your question, I think it would be very much an interesting future direction where we stratify these. However, based on the tools and criteria that Hyrule use currently, this is not something that we have done yet.
Yeah, specific medications were sticking out there too, like tiotropium. And that wouldn't necessarily be a word that I would associate with necessarily rigorous research. All right, next.
Matt Goldrick from Northwestern. This is really great. I think that we're using these to critique some of the models, and this is related to the point you just raised. Have you thought about going through and just censoring your data and removing all the drug names now that you know that it's picking up on that as a piece of data, and then re-performing the analysis to see if you actually get more robust performance?
Yes. Actually, relating to that, tiotropium, I believe, is typically used as a very common either intervention or control for RCTs in, if I remember correctly, pregnancies. Correct me if I'm wrong.
Yeah, it's basically another drug that you would, it's like another term that you would associate highly correlated with RCT.
Exactly. So that's perhaps one of the reasons why the model identified tiotropium as a term that is positively influencing rigor. And to answer your question, I believe that is certainly a possible thing that we can do. However, we do not necessarily have the data or the results currently, but it's definitely a promising future direction. Thank you.
Do we have any online questions since they didn't get to talk last time?
Yes, there's one in from Kathy Zeller, affiliation to be announced, is asking, from Boston University, can we imagine fraudsters using the results, the output of this study to create increasingly undetectable fake or shady studies, suggesting rigor, but not really having them?
This is a very good question. From my understanding, the training process of a deep learning neural network, such as the BioLink BERT model here, typically would not be able to be, I guess, controlled specifically during the process. So while it is theoretically possible to do that, practically, I do not necessarily see a way where perhaps individuals can deactivate certain neurons that would be beneficial for their own results for publication or other purposes.
Thank you.
In the back, please.
Really nice work. Randy Ellis, Harvard Medical School. So SHAP, like many feature importance methods, don't really get around the collinearity issue. And so I'm wondering if you saw a lot of co-occurrence or correlation between terms that might have high or low importance, and what maybe you or others could do to get around some of these issues.
Yes, I agree. This is the Collinearity is definitely an issue with SHAP and as well as perhaps integrated gradients and some other frameworks as well. I believe that the partition explainer specifically is designed for text, and it uses hierarchical clustering, which do take into account the collinearity between text in certain ways. But to answer your question, no, we have not done analysis on this, so this is not something that I can comment on.
Thank you very much.
In the front, please.
Markus Krivas, Helsinki, Finland. Thank you. Very nice. So where do you envisage that this will then be used? Because for example, if you work with PLUS and you want to do a systematic review on, say, let's take again the example of steroids and COVID, and there are 15 randomized trials. So going through those 15 randomized trials for you, I mean, that'll take a day or so, and your model will do it very quickly. But then again, in the whole process of getting this sorted out, getting the paper written, then is the day really going to make so much difference that this would be so valuable to you that it would give you much more information than actually reading the study yourself and making a sort of a conclusion? Is this a good randomized study or not? Will this inform practice? Because I sort of somehow see that the value here is the speed and the possibility to go through a lot of data. But the question that PLUS will ask for a given treatment will be very specific, and you will not have hundreds of thousands of trials. There will be a limited amount.
Yes, that is a very good question. I think in terms of on the model side of things, there are different ways that we can use a classifier model that outputs probabilities. Specifically for HIRU, we have implemented our model to where we set the threshold that achieves a 99% sensitivity, and we would only use the model for exclusions. For that model specifically, when we set the threshold to 99% sensitivity, we get approximately 64% specificity with a negative predictive value of around 97%. So if we only use it for exclusions, we're able to exclude more than half of irrelevant papers with approximately 97% accuracy. And this is where primarily the time savings come from. And of course, if you have rigorous studies where you have to read them, these models will not necessarily be improve your efficiency or accuracy in the same extent that perhaps a large language model would. But for the initial screening phase, these models do save a lot of manual efforts. And we have discussed internally that the number of errors that in terms of false negatives is something that we're willing to accept for the efficiency gains that we see from these models. And also in terms of the explanations, I can see that perhaps certain systematic review platforms that rank articles by relevance after you've screened a certain number of them implement something like this, so that when you do use these AI features, you can also see how they are actually, what terms they're using to ranking the articles and showing you the most relevant first. And that perhaps will give more reassurance to the reviewers.